Let's think about the collision between two objects. So let's say that A has a collision with B. So A was moving this way, B was moving that way. So A had some initial momentum, B had some initial momentum. And that after that collision, this is A has a final momentum, and B has a final momentum. While they're colliding, there is a force that A puts on B and a force that B puts on A, right? So during the collision, A is pushing on B. So here they're in contact with each other, and they're pushing on each other. So this is the force that A puts on B, A on B, and this is the force that B puts on A. We know about those forces that they're equal in magnitude but opposite in direction. Is that right? So how do those forces change the momentum of A and B? How is the momentum of these objects going to change as a result of those forces? Well, the change in momentum of A, right? The change in momentum of A will be equal to what? Let's assume that the force was constant, just to keep it simple. You don't have to write an integral all the time. The change in momentum of A is going to be equal to what? The force that is acting on A, the net force acting on A, multiplied by the time of the collision, right? That's our equation that we've been dealing with in this chapter, right? One of the important ones. That the change in momentum is equal to the force multiplied by the amount of time that that force was acting on, okay? So the change in momentum of A as a result of this collision should be equal to the force that B put on A multiplied by how much time the collision lasted, delta T of the collision. As I said, in an impact situation, the force is not going to be constant, it's going to be impulsive, but let's just keep it simple and just avoid the integral. So that's the change in momentum of A. What is the change in momentum that B is going to experience? The force that A is going to put on B, that's the only thing that is changing the momentum of B, multiplied by, is that time the same? It's a collision time, the time while those two things were touching each other, so it's got to be the same. Now what do I know about FB on A and FA on B? Equal but opposite, right? Remember that the direction is very important when we're dealing with vectors. So the equation that we have for B on A and A on B is that FB on A is equal to minus FA on B. Right? Newton's third law. So if I write that over here, what do I get? Let me call that force, the magnitude of it, let me call it F. So this is going to be F. Okay? So the force that B puts on A, let me call it, the change in momentum of A, it's going to be equal to the force that B puts on A, and that's going to be minus F times delta T. And the change in momentum of B is going to be F, equal magnitude, opposite in direction, times delta T of collision. So if A changes as a result of the collision, A changes its momentum by 3 kilograms meters per second, I know that the change in momentum of B is going to be minus 3 kilograms meters per second, right? It's got to be that way because they have forces acting in opposite directions. And the force multiplied by the time is the change in momentum. So notice that. So what happens if I add those two equations? So what do I get on the left-hand side? So if I add these two equations, this is going to cancel because that is the negative of this. So I get a 0 on this side, right? And on the left-hand side of the equal, delta PA plus delta PB, right? Equals 0. That's my new equation here. So delta PA plus delta PB equals 0. The changing momentum of one object is the negative of the changing momentum of the other. Why? Because the objects were interacting with each other. Nothing else was coming from outside to interfere. So I can write that equation in terms of PS, PF, and P initial, right? Delta PA is what? PA final minus PA initial plus delta PB, which is PB final minus PB initial. And I figure out that that should be 0, right? So what about I leave what has final on one side of the equation and what has initial on the other side? So PA final plus PB final should be equal to what? This one has a minus over here. So when I move it to the other side, it's going to be plus, right? PA initial plus PB initial, right? Okay, so what is that telling you? Yes, so the total momentum of the system AB, if instead of looking at A separate from B, you look at the system AB, right? Whatever happened there, that collision or explosion or something that happened there that involved force, action, and reaction, right? Whatever happened there, I know that for the system AB, the value of the momentum that it had before that happened should be equal to the amount of momentum that you have after that happened. Okay, so that collision or that explosion did not manage to change the net momentum of the system. It's the same before than after. Okay, so that's the statement of conservation of momentum, which says that if the system is isolated, meaning whatever happened in the system was one part of the system pushing on another part of the system, if the system is isolated, the momentum before should be equal to the momentum after. Now let's look at a slightly more complicated situation of objects that are interacting with each other. So the objects that I'm dealing with here are the pieces, the different molecules, if you want, of a ball, say a baseball. So molecule 1 is attached to molecule 2, to 3, and so on. There is some interactions going on, right? The different parts of the solid are attached to each other, putting forces. The molecular forces, I'm drawing them here with a spring, right? These are electrical forces that are holding things together. Now, suppose that there is another object that comes in and puts a force on your system. So my system is going to be the ball, okay? So to make matters simple, I'm going to assume that this bat is going to only put a force on 1. That when it hits the ball, it's only going to push on molecule number 1, right? It's in that region where the bat makes contact with the ball. That's where the force is going to be applied. That makes sense, I think. But I'm just simplifying it to one molecule, one object in that region. All right? So let's see what's happening here. What's happening here is that the molecules are interacting with each other, putting forces on each other. Force of 1 on 2, force of 2 on 1, and so on. Those forces are opposite in direction, equal in magnitude, right? So I'm going to look at what Newton's second law says for the motion of each one of these molecules in that system. So if I start with molecule number 1, okay, Newton's second law says that if I add all of the forces acting on that molecule, I should get the changing momentum of that molecule, dp dt. That's Newton's second law, right? F equals ma, or F equals dp dt is the same equation. I can do the same for molecule number 2. So now molecule number 2 is interacting with particle 3, so 3 puts a force on 2. Molecule number 2 is near 1, so 1 puts a force on 2, and so forth and so on. All of the neighbors put a force on molecule number 2. When I'm done adding all of the forces acting on molecule number 2, I should get the changing momentum of molecule number 2, right?
Don't the other molecules interact
With other ones?
Yeah.
right? So I'm focusing on molecule number 2. So I'm looking at the forces that are affecting molecule number 2, and they should be equal to the change in momentum of molecule number 2, right? So it's like I'm looking at you and saying the forces that you're having here, interaction with your neighbors, right? They determine how your momentum changes. So I add all of those forces, and they should be equal to your change in momentum.
They don't have to be directly touching the molecule.
There are forces between the molecules which are electrical in nature, so they're not directly touching, right? But there are forces that they're putting on each other. And those are these forces over here. All right? So I continue doing that exercise for all of the molecules of the baseball, right? I can do that, but then I start noticing that if I were to add all of the forces on this left side, everything that's on the left of the equal sign, if I were to add all of that stuff together and put it here, right, what would happen? The force that 2 puts on 1 is negative of the force that 1 puts on 2. So they cancel out, right? This vector is going to be the opposite of that vector. So when you add them, they cancel. The force that 3 puts on 1 is going to cancel with the force that 1 puts on 3. So those two cancel also. The force that 3 puts on 2 is going to cancel with the force that 2 puts on 3, which will be here, right? So everybody's going to cancel except for one guy. Which force is not going to cancel?
The last one.
The one that has no partner. The one that is the bat putting on the ball. The force of the bat acting on molecule number 1, right? So that's the only thing that is going to be left on the left-hand side of the equation. On the right-hand side, what are you going to have? I'm adding all of these terms, right? dp1 dt, dp2 dt, dp3 dt, and so on, all the way down to the nth molecule. So what do I end up here? The derivative of what? The derivative of the sum of all of the momenta. The derivative of P1 plus P2 plus P3 and so on, right? Because that's dp1 dt plus dp2 dt plus dp3 dt. So you're adding all of these terms, right? Now P1 plus P2 plus P3 plus Pn is equal to what? Is the total momentum of the ball, right? The total momentum of the ball. So what I'm saying is that when the bat hits the baseball, the force that the bat puts on the ball is going to be equal to the change in the total momentum of the ball. The change in the total momentum of the ball. Okay, I know that the ball is made of different molecules, and each molecule has a little bit of motion that might be different from the neighboring molecule. But when I add all of the momentum of the ball, that's my P total. That change in that quantity should be equal only to the force that came from outside. The force of the bat is the only external force acting on that ball. Okay? So basically what I have on the left-hand side is going to be the external force, right? And if the external force is 0, then you can tell from this equation that the derivative of the net momentum, of the total momentum of the ball should be 0. Okay? If that bat never hit that ball, this force will be 0, and the total momentum of the ball should be constant, conserved. Its derivative is 0, which means that its value is constant. It does not change, right? Now somebody might have put an explosive device inside that ball, and when the ball is sitting on a table, it might just go boom, and one piece of the ball might go one way and one piece of the ball might go another way, right? That's still satisfying the condition that the external force on that ball was 0. The force of the explosion is an internal force. Because that condition is satisfied, I know that before the explosion, the total momentum of that ball should be equal to the momentum after. Because momentum of the total amount, the total momentum of the ball should be conserved. So we're saying that only external forces can change the momentum of a system. Only external forces. The total momentum of a system. That comes from this equation, right? On the left-hand side, you have all of the external forces acting. In the case of the bat and the baseball, we only had one, but you could have more than one force pushing on the object, right? All of those, the sum of all of those external forces is what's going to change the momentum of the system as a whole. So this is how we're going to use conservation of momentum. The idea that the momentum before is going to be equal to the momentum after. How are we going to use that in problems? Well, if the external force acting on your system, remember, system is not just one object. System is a collection of objects. If the external forces acting on your collection of objects is 0, then the total momentum of that collection of objects is going to be constant. It's going to be constant. So when can you use the idea that the momentum is constant? When there's a simple system that you can find in your problem that it is isolated, right? If you identify a part of your situation where you know for sure it is isolated, nothing is coming from outside. Whatever happened was due to internal forces. If you can find that, for that object, you can do conservation of momentum. Another possibility is that maybe the system is not isolated, but what happened was that there was a collision or an explosion that involved impulsive forces. So remember, the idea of an impulsive force is that it's a very strong force over a very short amount of time. Okay? So we said that in the case of the ball hitting the ground and bouncing, right, the impulsive force was the normal, and that was a lot bigger than the weight of the ball. So during the collision, the weight of the ball can be neglected because the impulse of that force is tiny compared to the impulse of the normal force. Okay? So during that collision, you can ignore that there is an external force acting on that system, which is the weight of the ball, right? So the same situation would happen in a collision between two cars. Say a car is parked, another one comes from behind, hits it, they have a collision, and you're looking for the velocity right after the collision, right? During the collision time, the two cars have been rubbing on the ground, right? There's been friction between the tires and the road, right? But because there are impulsive forces involved in that collision, those forces are going to be a lot bigger than the force of friction with the road. So you can ignore friction during that collision and say that my system is isolated, that I don't have anything coming from outside. The road is not putting any force. And during this collision, I'm going to do conservation of momentum. The momentum of the cars before should be equal to the momentum of the cars after. And I will neglect the fact that there was a force of friction acting for a short amount of time. That would be a good approximation, okay?